Welcome, everybody. Learning as a hobby here. I wanted to go over section 1.4 in Theodore Shifrin's Multivariable Mathematics today. I'm going to make a push to, get to chapter 2 finally in this book because it's been a while since we did anything in here. So I want to try and finish chapter 1 this week, maybe. And I'm going to try and work on getting section 2A done in linear algebra done right also. So not today, but within the next week or so. So let's jump into Theodore Shifrin's book. I will bring my notes up here and we'll just go through it. This is kind of a long chapter, which is kind of one of the reasons why I was kind of putting it off, just because it's so long. But it's not the material is not that difficult. But I broke my notes up into two different things because I ran out of pages on the Jamboard because, like I said, there's just so much stuff in it. Section 1.4 starts with, excuse me, starts with the definition of a linear transformation, or sometimes it's called a linear map. So a function t from the domain Rn to the codomain Rm is called a linear transformation or linear map if it satisfies these two conditions. So if t of u plus v is equal to t of u plus t of v for all uv in Rn, and if t of c times v is equal to c times t of v for all v in Rn and scalar c. So with these two properties, what this is saying is T is a linear map if it preserves the linear structure of the underlying spaces. So meaning that linear combination, the map T sends linear combinations to linear combinations. All right, so that's the definition, and we'll look at a few examples of linear transformations in just a moment. All right, with this definition, it tells us that the values of t are completely determined by its values at the standard basis vectors. So, for example, if you know what t does to E1 and E2, etc., then you know what it does to everything because of the way we defined it. So, for example, every vector in Rn can be written as a linear combination of the standard basis vectors. So, for example, x is x1 times E1 hat plus x2 E2 hat, and so on, all the way up to xn En hat, where, for example, just in case you've forgotten, E1 hat is the vector 1 with all the other entries 0, right? E2 is the vector with a 1 in the 2 position, and all the other components are 0, and so on, like that. Those are called the standard basis vectors. Okay, so with that, if you take t of an arbitrary vector x, that's the same thing as t evaluated at this linear combination. And by the linearity properties, you get a linear combination that looks like this as the output. So notice that if you know what t does to the basis vectors of the domain, then you know everything about t. Right, so that's a nice property of linear transformations. So all you really have to know is what it does to the basis vectors. In particular, t of ej hat is given by some vector a1j, a2j, etc., all the way down to amj. Then we can associate in a natural way the matrix A to the transformation t. So the columns here would be, for example, this column would be t of E1, and the second column would be t of E2, and the last column would be t of En, and that matrix that's made up of those things is what we call the standard matrix for t, which we'll denote by t inside these brackets like this. Okay. All right, so now he just goes through some examples of linear maps. So the most basic example of a linear map, t from Rm to R, is t of x equals a dot product with x. So here a is some fixed vector in Rm, and if you evaluate the map t at the vector x, then what you do is you just take the dot product of x with that fixed vector a, right? And we can show that it's linear by just showing that it satisfies the two conditions. So that's what I'm doing here. And you can, I won't go through the details, but you can see, pause your screen and see all the details here. Furthermore, that means that the standard matrix for the transformation T is given by this 1 by m matrix, so where A1 through AM are the components of the fixed vector A. All right. Right, next example, consider the function T. Here, the domain of T is R2 and the codomain is R2, so T goes from R2 to R2. And what T does is it rotates vectors in R2 counterclockwise by 90 degrees. And you can figure out what the algebraic rule is for T by just using geometry. So if you have a vector, if you have a vector x here that has components x1, x2, then if you rotate by 90, that vector by 90 degrees, then the x1 component becomes negative x2, and the x2 component becomes x1. So this is the rule for evaluating a two-tuple at evaluating T at the two-tuple x1, x2. Right, and then you could check that this is linear by just seeing if it satisfies the properties, which I'm doing here. Again, I won't go through the details. You can pause your screen and see that here. And then also we can find what the standard basis is for the matrix for the operator T. I'm sorry, not standard basis, the standard matrix for the linear map T by just figuring out what it does to the basis vectors. So the standard basis vectors. So T of 1, 0 becomes 0, 1, and T of 0, 1 becomes negative 1, 0. And if you just put that into a matrix, you get the matrix for T. Right, another relatively easy geometric example here. Consider the function T from R2 to R2 defined by reflecting vectors across the line x1 equals x2. That's the line that makes a 45-degree angle with the horizontal axis and the vertical axis. And again, just by the geometry, you can see that the rule for T evaluated at the two-tuple AB gives you BA. So you just switch the x1 and the x2 components, right? Sort of like, when you invert functions, right? You swap x's and y's, which is equivalent to reflecting through the line y equals x. All right, and we can figure out the matrix for T by just doing the operation to the standard basis vectors. So the matrix for T is 0, 1, 1, 0. And you can, again, just check, you can check that this is linear by just checking the properties. And again, I won't go through that because it's relatively straightforward. That's what I'm doing here. So you can check that yourself. Right, part C, another example of a linear map, T from R2 to R2, where the matrix for T is given by the matrix A, which has components 1, 1, 0, 1. And geometrically, what this does is it shears R2. So for example, if you look at T of E1, it stays along the x1 axis. And if you look at E2, it gets sheared in to the positive E1 direction. Right, so this is called a shear. And again, you can check that this is linear, but I'll skip that just because it's just a simple calculation. Another example, there's a lot of examples that he shows here. So I don't want to spend too much time on any one of them because we'll be here forever. But example D, T from R3 to R3, defined by reflecting across the plane x3 equals 0. Again, you can just, figure out what T does to the basis vectors. That gives you the matrix. So here the matrix for that transformation has components 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Again, you can check that that's linear if you want to. Consider rotation of R2 through the angle theta given in radians. And again, you can figure out what the matrix is for T by just using geometry here, or trigonometry, I guess. T of E1, what T does to the basis vector, the horizontal basis vector, is it rotates by angle theta. This would be the angle theta here. which by trigonometry gives you the x component and the y component. The x component will be cosine of theta, and the y component will be sine of theta. And that's because the length of the vector here is 1. So the hypotenuse is 1. And then to find what t does to E2, you just use the fact that if you start at TE1 and rotate by 90 degrees, you should get TE2, right? Because everything's being rotated by the same amount. So E2 gets rotated by the same amount as E1 does. In other words, this angle here would, is theta. So if you just evaluate TE1 at the value theta plus pi over 2, and simplify using the sum formulas for cosine and sine, then you see that T of E2 hat is given by this vector here. So that gives us the matrix for T of theta. Sorry, T sub theta. So, the rotation through an angle theta clockwise by theta radians. Right, another example of a linear map. Just like I said, he goes through a number of these. So if L is a subset of R2, is the line spanned by the vector 1, 2, we can consider the linear maps ST from R2 to R2 given respectively by the projection onto and reflection across the line L. And here we're not he doesn't derive these in the book, he just gives you the matrices, but you could try it yourself using geometry to get the picture, and formulas from the previous sections that we did in the book. Like we have a formula for projection, for example. Okay, so these would be the matrices. And again, you can check that they're linear by just, checking the properties. Okay, so let T from Rn to Rm be a linear map. We want to define the product of the m by n matrix A with the vector x in Rn such that Ax is xj times aj, where j goes from 1 to n, which we want to be equal to summation j going from 1 to n, xj t of ej hat, which is t of the vector x. In other words, we want to define evaluating the linear operator or the linear map T at x by using matrix multiplication by its standard matrix. All right. So we know that what the columns of the matrix A are, they're T evaluated at the basis vectors. That is so here, if you look at this, the way that we wrote this out, that means that AX is the linear combination of A1, A2 through up to AN. Right, so that's the product of the matrix A with the vector X. Right, there's also an alternate way of viewing AX that allows us to interpret. Oops, I forgot the T here. To interpret AX equals Y as a linear system of M equations in the variables x1 through xn. You can think of it as the dot product of the vector x with the rows of the matrix A as opposed to the columns of the matrix A. So here, these are the rows of the matrix A. So not columns. Right, so you can get A times the variable x by taking the dot product of x with the rows of A, and that gives you this vector here. Okay, then he goes on into the algebra of linear functions. That, like I said, there is a lot in this chapter, so I'm gonna try to go through it a little bit quick because otherwise this video is going to be like 2 hours long. So the algebra of linear functions, so here's some important definitions that he gives. I probably should have underlined the words that he's defining here. Maybe I'll do that as I go along. All right, so the notation M with the subscript m by n, or m times n, it is represents the set of all m by n matrices. Here the m by n matrices were in this book. We're going to be assuming the entries are real numbers, but you could have m by n matrices of complex numbers, for example, or other things. So note that this set mn by n is this means isomorphic. We haven't talked about isomorphisms yet, but right now you can think of isomorphic. You can think of two sets being isomorphic. All that means is that there's a bijective function between the two that preserves the linear structure. So their linear structure is sort of equal in some way. Isomorphic. And you could see that by it should be natural how to do this. So if you have a vector in Rmn, right, that you have a vector with mn elements in it. Right, this is an Rmn. But you can write that as an m by n matrix, right? Instead of writing it as a column vector, you can write it as, a1, and so on. Just put in the entries into a m by n matrix. So you have m rows and n columns. So that's how they're isomorphic. It's just another way of representing the same thing. We can add matrices with the same dimensions and multiply them by scalars. So in other words, you could treat them, because of the isomorphism, you could treat the elements of m by n like as you would in Rmn, except like you're thinking of it as a matrix instead of a column vector, like I said. So you can add matrices together, as long as they have the same dimension, and you can multiply them by scalars. If m equals, excuse me, if m equals n, we say that the matrix is square. So if it has the same number of rows as columns, then we say the matrix is square. The entries with the same subscripts for rows and columns, A, I, are the diagonal entries of the matrix. And if Aij is 0 for all I not j, we say that the matrix is diagonal. So if the only possible non-zero entries are the ones on the diagonal, we say the matrix is diagonal. Right? If Aij equals 0 for I greater than j, then we say that the matrix is upper triangular. And if Aij is equals 0 for I less than j, we say the matrix is lower triangular. So just to give you maybe I should give you an example of an upper and lower triangular matrix. So for example, this matrix is upper triangular, whereas this matrix is lower triangular. Right? If S and T are linear maps between Rn and Rm, and C is a scalar in the real numbers, then we can form the linear maps C times T. So this is the scalar multiplication of the linear map T by C. That gives you a linear map from Rn to Rm, and also you can add the maps together. That gives you another linear map from Rn to Rm, which you could check by using the definitions here. So Ct of the vector x is equal to C times T of the vector x, and S plus T of x is equal to S of x plus T of x. Right? So these are linear maps also. Right, with these operations, the corresponding matrix operations are clear, just by using the definition of scalar multiplication and addition of matrices. But you do have to be careful. You can only add matrices when the dimensions match. All right, and then he has an example here. So let's C be the scalar -2, A be that square matrix there, B be the other square matrix, and C be the matrix 1, 2, 1, 2, 1, 1. So that's a 2 by 3 matrix. Then if you take the scalar multiple of A by -2, then all you do is just multiply each entry of A by 2. So -1 times -2 is -2, 2 times -2 is -4, 3 times -2 is -6, 2 times -2 is -4, and on like that. So that gives you C times A. And if you want to add A plus B, you can do that because the dimensions match. They're both 3 by 3. To get the entries there, you just add component wise. So for example, 4 plus 0 gives you the 4 over here. 1 plus 1 gives you the 2 over here. 3 plus 0 gives you the 3 over here. 3 plus -1 gives you the 2 over here, and so on like that. You just add component wise. Right. So notice that A plus C and B plus C are not defined since the dimensions don't match. So notice that, for example, A is 3 by 3, but C is 2 by 3. So the dimensions here don't match, so you can't actually add A and C together. And same thing with B and C. The dimensions don't match, so you can't actually add them together. The addition is not defined on those matrices. Okay, another important definition, the zero matrix is the m by n matrix whose entries are all zero. So for example, the 2 by 3 zero matrix looks like this. The 4 by 4 zero matrix looks like this. And so on and so on. So, any m by n matrix where all the entries are zero, we call that the zero matrix. Right? Let A, B, C in the set of m by n matrices. Let me erase these just so it's not confusing here. All right, so this is a proposition. So he labels this proposition 4.1. If A, B, and C are m by n matrices and C, D are real numbers, then we have some properties that addition of matrices satisfy and scalar multiplication of satisfies. So there's a commutative law for addition. There's an associative law for addition. 0 is the additive identity for matrices. The zero matrix is the additive identity. So if you take the 0, as long as the dimensions match, right? If you take the 0 matrix plus any other matrix of the same dimension, then it doesn't change the value of the matrix A. Right? There's also additive inverses. So for any m by n matrix, there's a matrix that we call negative A, such that A plus negative A gives you the 0 matrix, or the additive identity. Right? And then we have some similar properties for scalar multiplication. This is an associative law. This is a distributive law. This is also a distributive law. And this is multiplicative identity. Right? One thing to notice that there isn't here is there is no oh, actually, we haven't talked about matrix products really yet, so I'll hold off on that because he hasn't talked about matrix products here. But anyway, the operations that we have talked about satisfy these properties. Right. Next, we want to define matrix multiplication, and we want to do that in a way that allows us to represent composition of linear maps as matrix multiplication. So here, if S is a linear map from Rp to Rn, and T is a linear map from Rn to Rm, then the composition of T with S is a linear map from Rp to Rm, defined by T composed with S of X equals T of S of X. That's what composition means. We want to define matrix multiplication to correspond to composition of linear maps. So that's why we're going to define matrix multiplication in the way that we're going to define it, which you may be familiar with already, but this is why matrix multiplication looks the way it does, because we want it to have this correspondence with composition of linear maps. All right, so if A has, the standard matrix of T is the matrix A, is m by n. The standard matrix of the map S is B, which is n by P. Then the matrix C, which is the standard matrix for T composed with S, that should be an M by P matrix, and we define it by just using the properties of linearity. So T of S of EJ should be equal to T of T of I'm sorry, I'm getting tongue-tied here. T of S of EJ hat is T evaluated at the vector here, where this vector is S of EJ hat. Okay, and then just using the linearity that's equal to this. So it's the BIJs, you take those as weights for the linear combination of the AIs. So here the sum goes from I going from 1 to n, B, and then you just multiply each of the AIs by the scalar in the component BIJ, right? Where AIJ are the columns of vectors of A. So in other words, this is a linear combination of the columns of the matrix A. Right, so that's how we're going to define matrix multiplication, or one way that we're going to define it. The jth column of C is the product of A with BJ. Right. So let A be an M by N matrix and B an N by P matrix. Their product AB is the M by P matrix, whose jth column is the product of the entire matrix A with the jth column of B. That's the definition of the matrix product. That is AB, the ijth entry of A times B is AI1 times B1J plus AI2 times B2J, et cetera, et cetera. This is a dot product that gives the entry in the ijth position. Right, this is, oh, he's just saying what I just said. This is the dot product of the ith row of A with the jth column of B. Right, note that AB is only defined if A has the same number of columns as rows of B. Right, otherwise you can't do the matrix multiplication. And then this is what I was alluding to before, but matrix multiplication is not commutative. So there is an associative law for matrix multiplication, but there is no commutative law for matrix multiplication, which should be clear, because if the way that we define matrix multiplication, it corresponds to composition of linear maps. And if you remember, composition is not a commutative operation. Right. And then he has an example here just to get used to multiplying using this definition. So if A is the 3 by 2 matrix with entries 1, 3, 2, -1, 1, 1, and B is the 2 by 4 matrix with entries 4, 1, 0, -2, -1, 1, 5, 1, then A times B, when you multiply them out, I'll do a couple of the entries for you just so you can see. To get this entry here, you take the dot product of the first row of A with the first column of B. So here you would get 1 times 4 plus 3 times -1, which gives you 4 minus 3, which is 1, and that's where this 1 came from. Right? Similarly, if you want to take, let me color code this so it's not confusing. If I want to get if I want to get this entry here, let's do this one. So I want that entry. That's the dot product of row 2 of the matrix A with column 3 of the matrix B. So for example, 2 times 0, 2 times 0 minus 1 times 5 gives you 0 minus 5, which is -5, and that's where that -5 came from. And so on and so on. That's how you get all the different entries. Again, something to be wary of. Notice that A times B, we're able to do that product that gives us a 3 by 4 matrix, but B times A is not defined, and that's because the dimensions don't work. So for example, B is 2 by 4 and A is 3 by 2. Notice that the entries here don't, the dimensions here don't match. So 4 and 3. In order for the matrix product to exist or to be defined, these two dimensions have to be the same. Right? The number of rows of the matrix on the left has to be equal to the number of columns on the right. or sorry, did I say that backwards? The number of columns on the left, matrix on the left, has to be equal to the number of rows on the right. Sorry, that's the correct statement. Okay. Again, he has some examples here. So here, if A is the matrix with entries 1/5, 2/5, 2/5, 4/5, notice that A squared equals A. In fact, from that property, you can see that A raised to any natural number of powers is equal to A for all n. You can check that yourself by actually doing, and you should, by doing the product just to get practice with the matrix multiplication definition. He wants us to say what the geometric reason is for this. The reason is if you look at A times the standard basis vectors. So for example, A times E1, you get 1/5 times the vector 1, 2, and A times E2 is 2/5 times the vector 1, 2. Furthermore, if you take A times X, so let me just reposition here, A times any vector in R2, so if it has components x1, x2, that's equal to x1 AE1 plus x2 AE2, which is from what we just said about the standard basis, A times the standard basis vectors. That gives you x1 over 5 times the vector 1, 2 plus 2x2 over 5 times the vector 1, 2. You can factor out the common vector 1, 2. That leaves you with the scalar x1 plus 2x2 over 5 times the vector 1, 2. And this you can write like this. So it's x dot product with the vector 1, 2 times the square of the length of the vector 1, 2 times the vector 1, 2. And if you remember from previous sections, we talked about this. This is the projection of the vector x onto the vector 1, 2. So this is the projection of x onto the line spanned by the vector 1, 2. So that's why this is the geometry why it works, why A to the n is the same as A. And the reason for that is, once you project onto that line, then you can't, if you project again onto that line, you're still going to get the same vector, right? It's still going to be the same thing. So it doesn't change by doing it a bunch of times. So that's the geometry behind it. Right, he gives another example here from a directed graph in terms of the adjacency matrices here. I think I'm going to skip this example. You can read it in the book. It gives sort of I guess like a interesting application to matrix multiplication, where it counts the number of steps, the number of directed paths between nodes of certain lengths. So, but I'm going to skip this just for time. Because I don't want this video to be too long, and we still have a lot of stuff to do. So let me go. Actually, from here, I had to go to another Jamboard because I ran out of pages. So let's continue here with part 2. So here we start with another definition. The square matrix, which we denote I sub n, defined to be 1 on the diagonal and 0 everywhere else. So this is a diagonal matrix, in other words, is called the n by n identity matrix. And the reason for that is if you multiply any matrix by the identity, it doesn't change the value. So it acts kind of like the number 1 does for real numbers, but in this case, it's for matrices. Right, we have a proposition, some properties of matrix multiplication. So let A and A prime be n by n matrices. Let B and B prime be n by p matrices. Let C be a p by q matrix, and let C be a scalar. Then these properties all hold. So A times the identity is equal to A, and that well, A is not a square matrix here, so actually you have to multiply by the identity in different dimensions on either side of the matrix A, just so that the matrix product is defined. So A times IN is A, and IM times A is A. Right, property 2, matrix multiplication distributes over addition, matrix addition. And here you got to be careful the side that you multiply by B with, because remember, matrix multiplication is not commutative. So here, A plus A prime times B is equal to the sum AB plus A prime B. It's not equal necessarily to B times A plus B times A prime. So again, because multiplication of matrices is not commutative, so you got to be careful about that. But there is a version for multiplying on the left-hand side. If you have A times B plus B prime, that's equal to AB plus AB prime. So again, you just got to be careful about the order that you multiply in. All right, property 3, if you scale and multiply A, the matrix A by C, and then multiply by B, that's the same thing as multiplying A and B, and then scale and multiplying by C, and that's the same thing as scale and multiplying C by B, and then multiplying by A on the left. So that's a kind of associative law. And again, there's an associative law for, I mentioned this already, but this is an associative law for matrix multiplication. So if you multiply A times B, and then multiply by C, that's the same thing as multiplying B times C, and then multiplying on the left by A, right? So there is an associative law, but there is no commutative law. And then these properties just follow from the properties of linear maps and composition. So the proof follows directly from that, so we don't bother writing it out. Right, another definition. Let A be an n by n matrix. We say that A is invertible if there's an n by n matrix B, so that AB equals BA equals the identity matrix. B is called the inverse of A, and we denote it by A with a superscript of -1. So there's no notion of dividing by a matrix, but there's the notion of multiplying by a multiplicative inverse. So that's why we use that notation, right? Because just to make it clearer, if A is a matrix, 1 over A doesn't make sense. Right? You can't divide a number by a matrix, but you can multiply by a multiplicative inverse of a matrix. Okay, just a note, if A is the matrix for the linear transformation T, which goes from Rn to Rn, then A inverse is the matrix for the inverse function, T inverse. Again, that's a linear map between Rn and Rn. All right, here's some examples. So let A be the matrix 2, 5, 1, 3, and B be the matrix 3, -5, -1, 2. You can show that these two matrices are inverse of each other by multiplying them out. So if you take A times B, and you should go through this yourself, by doing the matrix multiplication for practice, but I just wrote it out here. So if you multiply A by B, you get the 2 by 2 identity matrix, and same thing if you multiply B by A, you get the 2 by 2 identity. So by the definition of inverses, that means that B is the inverse of A, the multiplicative inverse of A, and A is the multiplicative inverse of B. You can think of it either way. Right. He says in the book, it'll be convenient to have a formula for inverting a 2 by 2 matrix. So he gives us the formula here. So if A is the 2 by 2 matrix A, B, C, D, then A inverse is given by 1 over the determinant of A times the matrix D, -B, -C, A. That is provided that the determinant is not 0. Just so you can see that that works, maybe I will multiply this out just to show you that you get the identity. So if you take A times A inverse, this is A, B, C, D times 1 over det A times D minus B minus C A. And I can factor that scalar out in front. So this is A, B, C, D times D minus B minus C A. 1 times det A. If I multiply everything out, I get, see, AD minus BC, CD minus CD, minus AB plus AB, and then what's that? AD minus BC. Oops. All right, and just simplifying some things. Notice that's equal to 1 over determinant A times AD minus BC. Notice that that's the determinant of A, the way that we defined it. We get zeros here, and we get determinant of A. And then just doing the scalar multiplication, notice we get 1, 0, 0, 1, which is the identity matrix. And you could do it the other way around too. So you can take, A inverse times A and show that you get the 2 by 2 identity that way as well. And that verifies that those two matrices are inverses. All right, so now we have a formula for calculating the inverse of at least a 2 by 2 matrix. Okay. Next example, he says, we just want to use that formula. So A theta equals cosine theta sine theta minus sine theta cosine theta. This is, if you recall, we actually looked at this linear map already. This is rotation by theta radians in the counterclockwise direction. Right, if you want to invert this operation, we can use the formula that we just looked at a second ago. Notice that the determinant of A theta, the determinant of this matrix, is cosine times cosine, which is cosine squared, minus a minus sine squared, sine theta times sine theta, which is plus sine squared theta. And if you remember your trigonometry, cosine squared plus sine squared is always 1. So the determinant is 1, so I don't have to worry about dividing by it because it doesn't change the value. But I swapped the entries on the diagonal, and I negate the entries on the anti-diagonal, and then just using the even odd properties of the trig functions, that's equal to, notice, to cosine negative theta, negative sine negative theta, sine negative theta, cosine negative theta. Or in other words, this is rotation by negative theta radians. So in other words, what this matrix does is it rotates by an angle theta in the clockwise direction. So clearly that should undo what the first matrix does, right? If you rotate by theta radians and then rotate by negative theta radians, you end up back where you started. And same thing if you do it the other way. If you rotate by negative theta radians and then by theta radians, you end up where you started. So these two matrices undo each other, right? So that's just giving a geometric interpretation as to why this is the inverse. Okay, we can show that any two non-parallel vectors in UV and R2 spans R2. So this is just another application of matrix multiplication and inverses. Let A be the vector with the matrix with first column the entries of U, the vector U, and second column the entries of vector V. Then notice that the determinant of A, which is we define to be that u1 v2 minus vu2 v1. Notice that that's not 0. Therefore A inverse exists because because the determinant of A is not 0. And let's define C to be the vector defined by A inverse times x, so that has components c1 c2. Then if you take any arbitrary vector in R2, which I'm calling x, notice that that's equal to A times A inverse of x, because A times A inverse is the identity, and the identity times x is still just x. But then notice A inverse x we define to be the vector c, so that A times A inverse x is A times c, which from the definition of matrix multiplication, that's the linear combination of the columns of A. So first column is U, the second column is V, and the weights in the linear combination are C1 and C2. So you get the linear combination C1U plus C2V. Therefore, since X was an arbitrary vector in R2, we can write any vector in R2 as a linear combination of the vectors U and V. Furthermore, this representation is unique since x equals AC if and only if C equals A inverse x. If that's not obvious to you, I just did a very little proof here. He doesn't prove this in the book because it should be obvious, but if it's not, like I said, I gave a little proof here. So the statement is x equals AC if and only if C equals A inverse X. The reverse direction should be obvious, right? Because if you take A times C, so here, if this is true, then A times C is equal to A times A inverse X, which is X, right? So that direction is obvious. The revert for the reverse for the other direction, the forward direction, if X is equal to A times C, since A is invertible, that means that we can multiply both sides of this equation by A inverse, and that gives us A inverse X equals A inverse times AC. And again, A inverse and A cancel to give you the identity matrix, so that's equal to C, and that shows that the forward direction holds. Right, so that's a little proofing, just in case that's not obvious to people. Because like I said, he doesn't actually prove that in the exercise. All right, then he gives a proposition. I know this video is already feeling like super long, but there's only a little bit left to go. We have to get through transposes and this proposition that has to do with inverses. So this is a nice property. Suppose A and B are invertible n by n matrices, then their product AB is invertible, and the inverse of the product AB is given by B inverse times A inverse. So you have to remember to reverse the order when you're multiplying, when you're taking the inverse of a product. And we could just verify that that's true by just multiplying AB by the matrix B inverse A inverse on both sides. And here you could just see that, when you do that, you end up with the identity matrix. Therefore, B inverse A inverse is the inverse of the matrix AB. All right, last topic in this section, and then we'll be done with the summary at least. There are a lot of exercises in this section as well, so it'll take me a while to get through those and make the video about that. But anyway, we need a definition of what transpose is. Let A be the matrix Aij, be an m by n matrix. Then we define the transpose of the matrix A, which we denote by A superscript with a T. T stands for transpose, is the n by m matrix defined by just swapping the rows and columns of the matrix A. So A transpose is given by the IJ entry of the matrix A transpose is the JI entry of the matrix A. You just swap rows and columns. All right, so a couple more definitions. If A is square, then A is said to be symmetric if A transpose equals A, and it's said to be skew symmetric if A transpose equals minus A. Right, some examples here. Suppose A is this 2 by 3 matrix, B is this 3 by 2 matrix, C is this 3 by 1 matrix, and D is this 1 by 3 matrix. Notice that A transpose is equal to B because the entries of B, the columns of B are the rows of A, and vice versa. And C transpose is equal to D as well, because if you look, the column vector C is just the transpose of the row vector D. And then S here is just an example of a symmetric matrix. So if you take the transpose of S, notice that you get the same matrix back. So, if you take the first row here and turn it into the first column of S transpose, and you take second row here and write it as the second column here, take the third row here and write it as the third column here. Right, that's that gives you the transpose of the matrix S. But notice that the transpose of S is the same as the matrix S. So in this case, we would say that the matrix S is symmetric. All right. My voice is starting to give out on me, so hopefully we can get through the rest of this in a short amount of time. So proposition 4.4 says, let A and A prime be m by n matrices, let B be an n by p matrix, and let C be a scalar. Then there's some properties here for the operation of transpose. If you take the transpose of A transpose, that gives you the matrix A. If you take the transpose of a scalar multiple of A, that's equal to the scalar multiple of A transpose. If you take the transpose of a sum of matrices, that's equal to the sum of the transposes. And if you take, oh, sorry, there should be a transpose here. Let me just, sorry, this should be transpose here. If you take the transpose of a product, that's equal to the product of the transposes, but in the reverse order. So AB transpose is B transpose, A transpose, right? And just a quick proof of those things. Let me just see how much stuff do we have left here. I think there's an example and just a concept here. All right, here's the proof. So A transpose is equal to, just writing A transpose as the matrix Aij. That then if you transpose the matrix with entries Aij, that becomes the matrix Aji, and if you transpose that, that becomes the matrix Aij, which was the original matrix A, and so on like that. Maybe I won't go through all the details here because it's very straightforward. So you can read through, pause your screen and just read through the things here. Maybe I should go through 4 because that one looks slightly complicated. So here, for if you want to take the transpose of a product, if you look at the IJ entry of AB transpose, that's equal to the JI entry of AB. And by the definition of the, how we do matrix multiplication, the JI entry of AB is equal to the jth row of A times the ith column of B. And if you take the IJ entry of B transpose A transpose, again, just by the definition, the way we define matrix multiplication, that's equal to the ith row of B transpose times the jth column of A transpose. But the jth column of A transpose is equal to the jth row of A, and vice versa, right? And for B transpose, so you get the same exact thing. So all the entries are the same. Therefore, AB transpose is B transpose A transpose. And also notice if you check the dimensions, they work out. All right, so that's the proof of those propositions. All right, last thing here, we can represent the dot product in terms of matrix multiplication. So the dot product of X and Y is the same thing as the matrix multiplication X transpose times Y. And we have a theorem here, an important theorem. Let A be an M by N matrix, X in Rn and Y in Rm. Then if you take the dot product of A times X with the vector Y, that's equal to the dot product of the vector X with the vector A transpose Y. So if you want to move a matrix product across a dot product, you have to transpose the matrix, right? And the proof here is just, using the properties that we had before. AX is AX dot with Y from the fact that I have written up here is the same thing as AX transpose times Y. And then just using the properties of transposes, that's the same thing as X transpose A transpose times the matrix Y. Then I can associate, because there's an associative law for matrix products. That's the same thing as X transpose times A transpose Y. And then again, using that fact that I have in the box above, that's the same thing as X dot product with A transpose Y. And that's the proof. All right, and there is one last example, which has to do with an application, I guess, of transposes and so on. I'll just read it out real quick. I won't go into this in detail. It's relatively straightforward. It's just an application of the fact that we just talked about here. To manufacture the product vector X, which has components X1 through Xn, requires the ingredient vector Y, which has components Y1 through Ym. And let's say that X and Y are related by some matrix equation. So let's say Y is equal to AX. For some M by N matrix A, if each unit of ingredient J costs price Pj, then the cost of producing the vector X is given by the sum J going from 1 to M. This is a dot product here, Pj times Yj. Pj represents the price of Yj, right? So that's the dot product of Y with P, which is, since Y is equal to AX, that's the same thing as AX dot product with P. P is the price vector, right? P1 through Pj, through Pm. Right, and then just using the proposition that we just talked about, that's the same thing as X times A transpose P, which you can write as this dot, write out as the sum qi xi the sum qi xi, where I goes from 1 to n, where q is the vector A transpose p. The entries of the vector q is the amount it costs to produce a unit of the ith product. All right, so that's just that's the example that he ends the chapter with. Let me just stop my screen share for a second. Okay, so like I said, that was a long section, and you could hear it in my voice. I'm actually kind of sick, and I'm starting to lose my voice, which is great, right? I decided that I was going to do a video, a video a day every week, and then all of a sudden I get sick and lose my voice. It's getting kind of hard to talk now, so I want to end the video here. I will try to post a video tomorrow if my voice is feeling a little bit better. I think it should be. I should be able to post a video tomorrow, but I don't think I'm going to try and post any more videos today, just to save my voice up a little bit, because I think you could hear it already. It's kind of hard to talk. But anyway, hopefully you guys, it wasn't too annoying in this video with my voice like this. I will be posting the solutions to the exercises in Spivak and Shifrin, and what other exercise sets do I got to do? I got to do the exercise set for 2.2 in Taylor also still. It's been a while. And then hopefully I'll get around to chapter 2 in Axler. So anyway, let me know what you guys think in the comments. I'll see you guys in the next video. Until that time, keep learning, and I'll see you in the next video.